So welcome to the 2015 NASA Ames Summer Series. When we think of Saturn, Apollo, when we think of those missions in that time, we think of a great time for rocketry and space exploration. We also look at it as an era where we could do, and we do at this point, have a lot of lessons learned from. Complex machines were built to get us into space and have humans go to places as far as the moon. Today's talk, entitled Destroy Saturn V and Other Apollo Topics, will be given by Bill Colburn. It is actually quite interesting, the career of Bill's career. He thought of and looked at science fiction at the age of 11 and said, wow, I want to go into that area. Drive science fiction to reality, make it real. He enlisted in the US Air Force in 1954, still with the interest of following that dream. He worked for 3.5 years in NSA, serving the USSR development in rocketry. Then after that, went to Livermore, and then Ted Parker brought him over to the test range in China Lake. He was a staff engineer for Space Ordnance Systems. He has worked and designed and developed as part of the Saturn V, the propellant dispersion system, and the air abort launch. What is really interesting is he has made major contributions to complex systems. Started as a kid thinking about the approach and went through there going to a mission without the formal education that you would think somebody like that will have in a normal system. So following the dream is really important, and you could contribute to the complexity of missions like Saturn and Apollo and make history. So please join me in welcoming Bill Colburn.
Thank you, Dr. Cohen. Before any talk on Apollo, we really have to honor the 5 men who gave their life, 3 of which actually gave their life on a mission-related task, and that's Grissom, Chaffee, and White. So my heart to them and their heroic wives. Well, destroy Saturn V. Well, if Saturn V were this size, you'd use a Black Cat firecracker. You could blow that up easily. How about one this size? You could use 2 cherry bombs, but Dave would not like me to do that. So how about the huge thing? Look at this. But let me give you here I am. Dr. Cohen made a very nice introduction, but here I am on the Apollo Walk of Fame at Titusville, Florida. I'm the 3rd name on the first trident there. And looking at that, I thought, boy, that's really a great honor, until I realized, oh, it's in alphabetical order. Well, here it is, Saturn 1C. So Boeing comes to us when we were General Precision. We started as Precision Technology in Livermore with some very heavies from Lawrence Lab who started the company. Well, Boeing comes to us and said, we want to destroy this thing, which is 33 feet in diameter, the entire vehicle, of course, 360 feet long, 4,880,000 pounds of propellant in the complete vehicle. How do you do that without, say, taking out the entire Cape, taking out Cuba, which happens to be in the launch area, 44 degrees to 110 degrees. Cuba's right in there, and so are the Bahamas. Well, you don't want to do that, even though JFK might have thought, it's all right to take out Cuba, yeah. But so what do you do with that? 488,000 pounds, 4,888,000 pounds. That's the equivalent of 1 inch of propellant across 36 football fields. That's a lot of propellant. Okay, now what happens if that ignites in the air? 4.5 million pounds. What happens? 32 football fields, equivalent of 400,000 pounds of TNT. What is that like? There we are. Really not quite, more like this one. So, outside of protecting the any cities that you might be in the range, you want to get rid of everything before it has the possibility of going 350 miles to Cuba, 928 miles to the Bahamas, 960 miles to New York City. So let's get rid of it before it even has an opportunity to do that. Well, of course, they have the radar. And if radar detects any abnormality in the flight path, they can start a flight abort sequence. They also use a very interesting technique which had been used for tracking V2s at White Sands. And that was a wire frame. And the wire frame had two wires at an angle and then the optimum trajectory wire down the center. So the guy optically watched the vehicle. If it went outside of those wire defined areas, then that would initiate an abort sequence. Well, who was in charge of the abort sequence? I've read in some places that it was totally automatic. No, it was not automatic in all cases. It would be automatic if the wire running down the length of the Saturn V here and here, if those wires ever lost continuity, abort sequence would be automatic because that indicates a major rupture in a tank. Otherwise, the abort sequence was partially manual, and it was manual on the part of the range safety officer and on the command module commander. So, what happens, and how do you do this? Well, this is what we came up with Boeing. It took 5 pounds of high explosive to destroy the V2. And the Saturn V, we used 9 pounds of explosive to destroy the entire S1C stage. And how was that done? 2 runs of 175 grains per foot flexible linear shaped charge, which I'll show you how that works in a moment. And there were 40-foot lengths on each side of the Saturn V. On this model, they would be about half the size of a paperclip in cross-section, running 40 feet here and 40 feet here. The reason they were on opposite sides is when they did the ballistic calculations, if the propellants had mixed, then you would have had that subnuclear explosion. By ejecting the LOX out one side and the RP1 out the other side, you'd have less mixing and a much lesser explosion. Well, and those 2 FLSC lines shown here on their aluminum carrier, the rectangle on the outside, that's the channel that ran up. Again, as I said, that's about the size of half of a paperclip. It would run up the side here. That was 2 inches by 1 inch, just to give you an idea of the scale. And inside of that was an aluminum carrier that had that shape, and the red parts are the FLSC that were bonded in place there. Now, this is an interesting assembly because everything was done with adhesives. There's not a single mechanical joint in that propellant dispersion system, which is extremely interesting. Even the Skunk Works, I understand when they used adhesive, they always put in what they call chicken rivets just to make sure that their adhesive doesn't fail. This entire thing was held together with adhesive. It was a urethane that was qualified to minus 280 degrees for the LOX tank. So what happens? Well, when we initiate that, this is what happens. It cuts a 1 inch wide gap in the 2019 aluminum tank structure. And you see the little ribs in that tank? That's an amazing thing. We may not be able to make a tank like that right now. That was made by taking enormous sheets of 2019 aluminum and then milling a pattern to reduce the wall thickness but retain the ribs for stiffening. That was about roughly 1/4 of an inch in the thin section and 1/2 an inch on the ribs. And then they would roll that and weld that into these enormous tanks that were 33 feet in diameter. Incredible technology. Now, so now we have that happening. We have the propellant squirting out each side of the vehicle. But wait a minute, we forgot the astronauts in the command module. We can blow up the S1C and the upper stages. That's fine. But how about these guys up here? We got to get them out of the way. Well, already they had the escape tower and the escape rocket designed and built for emergency abort from the pad. Now they wanted to determine if they could also use that in various stages of altitude and velocity. Incidentally, the Saturn V manual calls this a small rocket. This rocket had 147,000 pounds of thrust for 4 seconds. I don't call that a small rocket. That's 3 times the thrust of the V2. And that burned, as I said, for 4 seconds. And that would, from a standing start, that would take the command module to 4,100 feet in 11 seconds. So they determined that with the manual, even with the manual abort, they could get the command module far enough away that the ignition of the RP1 and LOX would not affect it detrimentally. So then what happens? Well, canards pop out. If it's a low altitude abort, canards pop out, and the canards veer the command module away from the direct trajectory of the vehicle. If it's at high altitude, there's a pitch motor, a small solid propellant pitch motor. So if it's at 280,000 feet, which is the maximum feet for an abort, the pitch motor would tilt the command module and get it out of the way. Then they would fire the bolts that held the rocket tower to the command module, and that would pull off the ablative heat shield. There was an ablative heat shield over the forward heat shield. Pull that off. Then they had to get rid of the forward heat shield because that was covering up the parachutes. So let's use the parachutes next. All right, that's a very good idea. Then the drogue mortars would fire. The drogues would go out. Reefing line cutters would open the drogues, and then the drogues would pull out the mains, and you'd have a recovery. Now, boy, how did they know that was going to happen? Oh, this is the CDF carrier, incidentally. This is CDF, a confined detonating fuse. It's a 2 grains per foot. It looks like solder. Looks just like a little lead solder. And 2 grains per foot. That was inside of a polymer coating, and then the polymer had fiberglass tubing over that, and then another polymer coating, and then another layer of fiberglass. So when the confined detonating fuse detonated, and that's detonation, that's extremely rapid process, the detonation would be completely confined and wouldn't disrupt any of the mechanical or electronic components nearby. The CDF is what started most of the processes on board the Saturn V and aboard Apollo, because it was virtually instantaneous at 8,000 meters per second. That's pretty fast. So and the CDF in all cases was initiated by what's called an EBW detonator. That's exploding bridge wire detonator. And the reason they used exploding bridge wire detonator is completely insensitive to electrostatic discharge, completely insensitive to low current. In fact, you could take an EBW detonator and plug it in the wall, and it would not initiate. It would fizzle and burn, but it would not detonate. So they used EBW detonator, the safest possible way to initiate the CDF and initiate all of the various functions that had to happen in the stage separation, the command module separation. The docking ring separation was also done with detonating cord. So here we are. We've protected the astronauts. We've dumped the propellant. we're pretty safe. This is the crossover. We're talking about the CDF. And you notice the manifold paths. We have 2 CDF lines coming in, simple redundancy, but each line has a crossover, so we have double redundancy in this connector. We have 2 FLSC runs, pretty much a very high reliable system, because if any one of these paths failed, you'd still initiate both of the FLSC lines and you'd still cut the tank. And that's extremely important, because one FLSC line would not open the tank. It would just make a slit and it would dribble out over time, but it would not be a true abort. That's a CDF connector. That has a curious thing. It's a spring-loaded lock, if you see the grooves on there. And that was, as far as I know, that's peculiar only to CDF connectors. I haven't seen it on a hydraulic system, for instance. Now this is moving over to the rest of the Apollo pyrotechnic systems. This is the basic standard for initiating nearly all of the pyrotechnic systems outside of the EBW. And that's called the NASA Standard Initiator. The last I checked, this has a reliability of 595 at a 95% confidence level, which is astounding. And so that may be the most reliable component in the entire, oh, except maybe a few resistors, yes. So here's how we determined if that escape system was going to work at altitude and at velocity. The little Joe. There's the little Joe. You can't quite see it, but in this mock-up in a rocket graveyard, the nozzles are put in upside down. But there we are. So that's the little Joe. That was 86 feet tall, 8.5 feet in diameter, and look, 176,000 pounds. Pretty big rocket. It had a couple of Algol motors, and then I believe it had different combinations depending upon what the mission called for. That was, for all of you model rocketry people, this is the world's largest clustered high-power rocket. And there it goes. Now, at altitude, what would happen is they would go through all of the abort functions at a different altitude and different velocity. In every case, the command module was recovered safely. In fact, in one case, the little Joe, due to a problem in the flight computer, the little Joe exploded. And so they had a real emergency, and the command module safely recovered even in a real emergency. So they counted that as sort of an unexpected win. Now the little Joe, we mentioned the drogue mortars. The drogue mortars, what I'm going through is in my personal history, so it might be a little disconnected to you. But the drogue mortars had reefing line cutters. The reefing line, what the reefing line would do, it would hold the drogue closed for 8 seconds until everything became stable. Then the reefing line would cut the reefing line. The reefing line cutter would cut the line, and the drogue could open fully. And then after that point, at the proper altitude, the drogues would pull the mains out, the 3 main chutes. Now, to remove that forward heat shield, we designed this, the Type 6 pressure cartridge. Now, High Shear had tried, this is an amazing cartridge because it produces up to 20,000 psi in a plenum. There are 2 half-inch stainless steel tubes that run off to essentially pyro pistons, and those pistons force the heat shield off at 80 feet per second. And that's a 280-pound heat shield, so that's a lot of force. If any two of these cartridges fired, the heat shield would be ejected safely. And the reason you wanted to get that velocity is you didn't want that forward heat shield, 280 pounds, to come back and hit the command module and perhaps injure it in some way, like the heat shield, its own heat shield. So there were four of those and four pistons that ejected the command module forward heat shield. And the Type 6 pressure cartridge had a, since it was so unusual, it had to produce that 20,000 psi in a few milliseconds. So it was what we would call brisant. It was a very rapidly operating cartridge, so high burning rate. The burning rate of the propellant we used at this pressure was 1,600 inches per second. That's unheard of in solid propellants. But we used permeable burning to get that rate. And we're talking a 5-inch long grain. That 5-inch long grain would burn in a couple of milliseconds. Amazing. And in order to ignite it, since it had a very high, it's called burning rate, the burning rate exponent. The burning rate exponent of a good propellant would be around 0.25, 0.3, 0.4, means that's its sensitivity to pressure. This propellant had a burning rate exponent of 0.83, means that it's highly sensitive to pressure. So because of that, it was prone to what we call a DP/DT failure. That's the rate of pressure drop. If you had a high rate of pressure drop, this propellant could quench because of its high burning rate exponent. So what we did to ignite it satisfactorily is we had a two-phase opening of the closure, and that's a chemically milled closure, which was a first at that time. So the light gray area would open first. We're talking milliseconds now too. The light gray area would open first, then burning would be established while the other petals were still there, and then they would open, and you'd have the continued burning of that grain. Type 6 pressure cartridge. So the docking ring had to be beefed up for the docking ring had to be beefed up for the to separate the limb. Originally, it wasn't strong enough. So just before before Apollo 8, they had an emergency development to develop a long-reach detonator to fit in the new docking ring. Well, we did that, and very simple. We just added an extension, but that extension couldn't be filled with explosive because then it would be too much explosive and it would have distorted the ring. Not a good idea. So that's a long-reach detonator. So it had essentially what we call a flash tube from the NSI to the explosive. It was just an empty tube. And then the through bulkhead escape motor. Yes, okay. For maximum reliability, we decided not to use a glass seal or a ceramic seal, although they work perfectly well in most rocket motors. This was a metal-to-metal seal, so there were no, everything in that rocket motor was metal-to-metal sealed. And this is how that works. If you see, the upper part of this drawing is where the CDF connector attached. And that CDF initiated the first little red zone. That's a PETN explosive. The shock wave would go across the little bulkhead, and that shock wave would initiate the second PETN charge, and then that would initiate the output charge, which would start the rocket motor. And that's a through bulkhead igniter. And I think we're going to have a lot of time for questions here. Dr. Cohen?
So, thank you very much. So we have time for questions. If you have a question, please raise your hand and wait for your the microphone to get to you. One second.
How much of this did you design yourself, of these devices?
I'm sorry, can you,
I can repeat it
How
if you
many
want.
of these devices have you designed yourself?
oh, all of them, excepting for the NSI. I did not design the NSI, but everything you saw here, I designed, yes. And followed through production. In some cases, hand-delivered, hand-delivered to White Sands in time for the Little Joe 2 tests. We hand-delivered the first FLSC to the Cape, not to the Cape, that was the F series, the F500 series, which was a fit-up. I assume F stands for fit-up. And we delivered the propellant dispersion system to them for a fit-up. Incidentally, that 2-inch by 1-inch aluminum rectangular tube, that was slotted at intervals to take care of the contraction. As the LOX tank was filled, the tube, of course, would contract a couple of inches, and so those slots would aid in that contraction. Well, they forgot to take when they milled through, they didn't deburr the interior of the slots. So when we tried to insert the FLSC carrier in, it got halfway in and stuck. Well, good thing they did the fit-up test first. So after they cleaned those all out, we were fine. But we also had, the specification was for 220-pound pull. We had to make connectors like this that would take 220 pounds to connect each 4-foot length. So we'd have 10 4-foot lengths connected like this. 220 pounds was not enough, even though that was the specification. So we changed that. We put a single bar of A286 steel with an eye at one end and a hook at the other end, and that had probably a breaking strength of maybe 3,000 pounds force. I hope that answers your question.
I understand that before the shuttle project was started, the goal was to have no pyrotechnic devices on the shuttle, and it ended up having over 300. I was wondering, it seems to me that pyrotechnic devices have the highest specific power out of any way you can actuate or ignite, and also the reliability is extremely high. Why would one not use pyrotechnics? It seems like a good approach to me.
Probably because of the regulatory problems and the fact that when you arm pyrotechnics on a launch site, then everybody else has to clear away. And so when the pyrotechnic is armed, that's a specific safety condition and you have to observe that condition. So if you don't have them, maybe it's a little better, maybe. But you're right, reliability is incredible.
Thank you. Very interesting talk. Did North American design the first stage, and how many detonation tests were run, and was any type of stress analysis done during the development, or was it more of a trial and error process?
Yeah.
So could you repeat that?
Did North American build the first stage? How many detonation tests were done? And was any stress analysis done in the development, or was it more of a trial and error process?
So did North American build the first stage? How many detonation devices were used, and was any stress analysis done?
Oh. Well, if you look at the NASA SPs of that era, oh my heavens, yes, stress analyses were done. There's an SP for almost every type of structure, you know, conical, cylindrical, whatever. So yes, I'm sure stress analyses were done. There's also pyroshock, and pyroshock was a major problem. In fact, it's been a problem in some of the, I believe maybe on the Mars Observer, possibly. And So a lot of studies were done on pyroshock. And Larry Beament was at Langley, and Larry Beament was responsible for really bringing the pyro black art down to a science. And if you look up some of Larry Beeman's publications, you'll see that he did an excellent job in that arena.
Hi, Bill. I know Bill. He's a great guy, and I've been down to his shop in Hollister, and my question is, you've worked on a lot of these projects for this program, but currently you're still designing various rocketry programs at your offices in Hollister. Can you just give us a real quick, brief description of what you're doing down there now?
Okay. Do you want a check or money order? Well, thank you, Charlie. Yeah, Charlie has been to our, what we're doing in Hollister, we're working on hybrid propulsion systems. And in 1951, this little rocketry group we had in Watsonville, California, fired a hypergolic hybrid, probably the first one ever. And we used a German oxidizer, which is 90% nitric acid, 10% sulfuric acid. Since it had sulfuric acid, we knew that it would react with potassium chlorate, so we put a little potassium chlorate in the asphalt, and we had a hypergolic hybrid. So what we're doing is since hybrids are incredibly safe until they're loaded, as are biliquids too, they represent an arena between an area between solids and liquids, and they have about half the complexity of a liquid. So they're kind of attractive from that viewpoint. ISPs. My partner is a Harvard chemist, Ron Winston, and he has developed several propellant additives which boosted right over 300 seconds ISP at sea level. So that's pretty incredible, and that's what we're working towards, is very high ISP hybrids. That's it.
Thank you.
Hello. How did you guys validate the analysis for the pyrotechnics on the stages for detonating stage on abort?
Whoops, I didn't hear that one.
So in terms of the analysis of coordinating the pyrotechnics on the stages, how did you verify them?
Well, that's Larry Beeman's favorite subject because Larry called what we did black art, as I mentioned before. And we did, what we would do, instead of approaching it analytically, we would do off-limits testing, qualification testing. So that's primarily how the pyro systems developed. So off-limits testing would be, we would change the loading until it didn't work on one end and it worked too well on the other end. And that's the extent of it. Very, very little analysis. Now it's quite different since Larry attacked the problem some 25 years ago.
Appreciate the discussions. Your comments on Little Joe kind of reminded me of a long time ago where Little Joe in an associated program called Little John was going to be used not for space, but actually to a very multiple numbers of Little Joes or Little Johns to actually thrust and change the rotation of the Earth in an event of a nuclear exchange. Do you have any comments on that or remember that at all?
Approaches of using like multiple Little Johns and Little Joes
In the realm of my interest, but way outside of my expertise, sorry.
So I have a question. I don't know if my mic is up now. So the question is in terms of risk culture. So, you know, when you look at the era of Saturn and Apollo, you see that there were accidents that occurred both with humans and without humans. But you saw a progression of the rocket's design, the systems, whether it's... and so on your stage of engineering, how is the culture of risk then, in terms of the ability of taking risk to develop new technologies to move forward, versus now as a culture that is, whether it's within NASA or the industry that you're working on, in terms of that? Are they the same or different between those two?
Quite different, Doctor. We had a whole section of designers, and the designers were familiar with mil specs, for instance, that we didn't have to bother with. So if we wanted to use a certain bolt, they'd, no, you can't use that bolt, you had to use this bolt. And so we had that kind of support. We had a secretarial pool, and so that took another load off of us. So we were free pretty much to Imagineer our projects. The advent of the computer changed all of that, and now each engineer is his own draftsman, drawing guy, secretary, you know. So yeah, it's considerably different. I think that an engineer now needs to have more skills than we had. We were a lot more focused, though. We were, I think, far more focused on the job than you can be now, because you have to have this wide panorama of skills. So that would be my answer.
Okay, so please join me in thanking Will Colburn for an excellent seminar. Thank you. Thank you very much. Thank you.